Hello everybody, welcome back to mass spectrometry. We are going to have alcohols for you today served. It's on the house. Let's go. Let's see what all these alcohols are going to get fragmented into. So it's fragmentation patterns of alcohol. So coming up, alcohols. All right, what can alcohols do when it's inside a mass spec machine? What's going to happen inside the machine when it's traveling through? It's going to go through and it comes in a kind of a clump, then it gets spread out in the vacuum chamber, and these individual molecules then keep moving real peacefully and then get get beaten. They get struck by lightning, right? Electrons, ionization. Electron ionization typically will pull out electrons from the molecule, especially where it's loosely held. And in this case, it's a lot easier to take it off of the oxygen than the sigma bond. So that's what happens as soon as you put it through the machine and it gets hit by electron spray. Okay, so one of these electrons is going to get taken out. So let's say you hit it with electron ionization, and it takes that off. Now you're going to get a cation and a radical on the same molecule. That's called a radical cation, which you only see in mass spec. Okay, so these are all theories of what could be possible. And here we took out that electron, and there is a plus. So this is your radical cation. Okay, you could also write it out like this. You could write down the molecule because, and put it like that. Okay, now we're going to take a journey through the machine with this and see how many ways you can fragment it and what do these numbers mean. Okay, so we have 87, 84, 69, 57, 45, 43 proof alcohols. Let's see what they are. Okay, let's start with our highest peak here, 102. If you count all these up, 102. So that's just Z is equal to 1, M is equal to 1/2. So this is your M/Z number. So we'll take that and run with it for right now. See what you're going to get. All right. Okay, so what are the things that could happen to this molecule when it's going through? And I'm just going to label this A, B, C, and so on. Let's say, so here, because these are different pathways. And sometimes this would go over here, and this would get broken up into smaller pieces and so on. Okay. All right, so let's do it. So here we are. We have a hole here and a radical, and you don't have to always write it out there. You can write out the hole over here because, again, it's all on the same oxygen. Now, you have over here, as soon as you do this, these alpha carbons or the carbons next to it become really very vulnerable because the oxygen's pulling electrons there to fill up the hole. So it can fragment right here. So that CH3 here can get taken out, and these can go in to form a double bond. Okay, so that is going to be the fragmentation pattern for this molecule initially. So here's a double bond. Now, the oxygen, and we shouldn't ever lose track of formal charges. There's a hydrogen here, and here is your radical. So we took out 15. So 102 minus a 15 is going to be 87. So this is your 87 peak. And if you look at the oxygen here, you have 1, 2, 3, 4, 5 for formal charges. So 6 minus 5, oxygen's group 6, is a +1. So you should put a positive on the oxygen, which is then going to get accelerated through those plates and hit the detector, and it's going to pile up on 87. So the junkyard guy is piling these cars up, okay, according to mass. So this is their 87 pile. Let's see what else can happen here. Okay, so that's, we took out a methyl, and that's 15. So the next one is 84. Well, 102 minus an 84 is 18. So it's unlikely that it's going to be a hydrocarbon, because we saw earlier when we broke up hydrocarbons, it was 15, 29, 43, 57, and so on. So therefore, it's unlikely that it's a hydrocarbon. It is probably, and 18 is a very common, molecular weight for water. So let's see how we can take water out of the molecule for this other peak, okay? 102, typically alcohols lose water, very quickly, so which is why your molecular ion peak is so small, okay? So let's look at B again, how we can take out water. So here is your molecule, and we're going to start again from the radical cation. Okay, so here is our oxygen with that unhappy unpaired electron. This is looking for a pair or a mate. All right, well, over here, if you take this out, that'll be 17, and we don't really see too much of that. There is a tiny bit, but it's more 84, which means water molecules going out. So it's getting a hydrogen from somewhere. Where do you think it's getting that hydrogen? If you look at that molecule, here's a tertiary center. And so if you make a radical there, that would be pretty stable. And so the molecule always has this internal intelligence or knowledge about its stability and goes toward it. And here, I'm not going to put equilibrium arrows, because once it's gone, it's gone. It's history, okay? There's no equilibrium reactions for the most part. It just, gets sucked out. Once this goes, you can't bring it back and make this, all right? So that's why I'm not putting equilibrium arrows, as you can see. So here is our oxygen then getting that hydrogen, and I'm just going to draw that in a different color. And you have a lone pair there, and you also have another hydrogen here on that oxygen, and you have a radical, okay? And if you look at the charge of this molecule again, 1, 2, 3, 4, 5. 6 minus 5, is 1, so there is a charge here, which means it's to go, all right? So here, this is going to take these electrons and disappear with it. So that you have then a radical cation again. So you take out that oxygen, you are going to get a hole here, and the radical is right here, okay? And water is going to be neutral, because you have a lone pair that's coming back here. So you have 2 lone pairs now, and so therefore you are going to get a beautiful water molecule. These 2 electrons are going to go with the water. This is 18, and so 102 minus 18 is going to be 84. All right, so we have 87 peak, check, 102 and 84, check, done. Let's move on. You can see this is your molecular ion peak. I'm just going to put MIP for that, so I don't have to write it over and over again. And here is our base peak. That means this is the most stable of all of the fragments, and so it's formed in higher quantity, or the fragmentation pattern favors the formation of this. Let's see what it is, okay? All right, so here we talked about this molecule getting fragmented on this side. Alpha fragment. So here alpha fragmentation happens on this side. What about here? Well, let's check it out. Maybe that's what it is. We don't know until we do it and check it out. So let's do it. In fact, it might be better to do it here than here, because here you're going to get a more stable radical than here. So over here, your radicals here form a bond and kick this guy out, which means you are going to form a radical here, plus you would form a double bond oxygen, and there is a hydrogen on it. This lone pair is unaffected, at least in this reaction, the way we've drawn it. And we can again check out your formal charge. 1, 2, 3, 4, 5. Supposed to have 6 on the periodic table. Got 5, so formal charge is going to be 1, which means we have a positive here. And that is your biggest peak. This is 57. We know 4 carbon fragment is 57. And this is 45. If you add these two, you would get your molecular ion peak, 102. All right. Let's look at how, well, right next to that, it's got a little brother there, 43. How do you think that could happen? 2 difference. I mean, what can you take out for 2? Obviously, there's no helium. I mean, there's no carbon, oxygen, or any of those getting out. 2 would only mean 2 hydrogens. Where do you think we can take them from? Well, maybe we could consider getting 2 hydrogens off of here. And I'll rewrite this just, as a way of doing the mechanism again for that. So here is a hydrogen here, and now I'm going to draw the hydrogen on this side. Here's our positive, and here's your lone pair. And there's a methyl here. So if you take these 2 hydrogens out, that would give you a 43. And chances are, if that's our hypothesis. Let's work it out, see if it works. So here, this is a covalent bond, and each of them has 2 electrons. And if you want to make a bond, you need 2 of those electrons. The hydrogens obviously are happy together. So your hydrogen gets out as a gas, out into the atmosphere, and you can have a triple bonded carbon, which means that would be an sp3. You still have a lone pair, and that's your molecule. Well, let's look at the charge. 1, 2, 3, 4, 5. Again, 6 minus 5 is 1 on that oxygen. So you have a positive hole on that oxygen, and that is going to be recorded on, and it hits the detector as a peak, and it stacks up and up and up, and you get 43 plus 2. Okay, so 45, which is the same as this peak here, going down here. All right, so we kind of did a lot of these peaks, but we do have 2 here. 69, which we hardly ever see. 57 we've seen before, and that's a 4 carbon fragment, right? So let's look at what could possibly give us 69. Well, how would we go about thinking about it? First of all, we can think to see if it is just a methyl leaving from one of these bigger fragments. So if you add 15 to the 69, that's going to give us 84. So most probably that's what happened. So here, 84 is going to lose a methyl and give you 69. All right. We already saw that 102 lost a methyl and gave us 87. And 102 lost water and gave us 84. And we also saw that this is broken up in two, and you get a 45 and a 57, right? So now let's look at how 84 can become 69 by methyl loss. This is your 84. So this is possibly, the molecule that's going to break up to give you 69, okay? So let's go over here. So here we've already done, check this out, check this out. All right, let's go on to see what these could be possibly. So if you take your 84, 84 is just a cation right here with a radical. This carbon here has only a formal charge of 3, 4 minus 3 plus 1. And there's a radical from pulling off the hydrogen over here. So, well, if you want to lose a methyl, you would have to then get rid of this. Because if you have a methyl radical going over here, that's not going to, you have a radical here. So that's not going to be possible because you'd have, sorry, John, sorry. So I'm going to start from, let's see how this is possible. Okay, so here, we have over here a molecule that has a methyl here, and that could actually then go over and give you a radical cation. All right, so if you go over here, you are going to get, okay, John, give me a minute, okay? Give me a minute. I don't want to edit it, so. So we can split up this bond between these two, and you can get over here a radical, over here. And well, even if you have a radical, we started off with a positive charge. So that is going to have a formal charge of, again, a positive. This is going to go away as a methyl radical. So if you take your fragment that was 84 and take off a 15, that is going to be 69. And this is your 15 fragment. So this is your M over Z 69. All right. Now, some books have put these together to make a triple bond, which would be kind of rare because triple bonds aren't really very stable. But I've seen that. Okay. But this is fine. That's your radical cation. All right. Let's look at how you can form 57. So same thing. 57 is if you take 84. And if you 57 is actually about a 14. John, sorry. Let me do this again. Okay. All right, let's look at how we can do a 57. Well, we broke it up here, but how about we break it up here with this 4 carbon fragment can be 57. Let's try that out. Let's see what happens, okay? So let's take this fragment over here. So here, after your water leaves, you can get an 84 here, and your 84 fragment is going to then break up to give you, more fragments. So here is your CH3, and you have a hydrogen, and you have a positive. And we do have over here a radical. Now, if you take this molecule and you take these 2 electrons over here, all right, so let's see how we can break that up. So if you take this, I'm going to redraw this to another possibility here. So here is your methyl group, and you have a hydrogen here. And you can take that hydrogen over here and make a radical over here. Now remember, there is a positive charge there. All right, so here is our hydrogen hopping over, alpha, beta, gamma, and you can do that. And so here you can have a positive here and a radical over here. Now, if you take this molecule, you can see how this is all set up now to go away as a 4-carbon fragment, a cation. So you can take this and move those electrons over, move and break it up. And if you do that, you are going to get this fragment here going away and the positive charge as a neutral, and this would be your positive. Okay, so over here, you could think of one of these forming a double bond there, and giving you a fragment where you have a radical, and you can think of this part becoming a cation. All right, and this is primary. It's possible here to go to a tertiary, so, and that would be very stable. Okay, so that would become your 57. And so here we started with our 84, and we took away our fragment here, and that is going to be your 54. This is going to be a 27. 24 plus 3, 27. That's your neutral. Okay, that's going to get sucked in through the vacuum up, and the cation then goes and hits the detector and gives you this peak. Okay, so we pretty much looked at all of them. 57, done, and 69, done. So here's just a very brief description of what could happen to an alcohol inside a mass spec machine. All right, we'll see you with other functional groups. Now, is this always the case with alcohols? Well, you could always think of water loss on an alcohol. You could always think of alpha fragmentation, fragmentation right next to the carbon bearing the oxygen on alcohols. And you could also think of, then cations, then fragmenting. But these patterns you would see in most alcohols. Water removal, alpha cleavage, and so on, hydrogen elimination, and so on. So these are things that you would see over and over again. All right. Now, when you're doing a mass spec, it's always good to do a mass check before you finally, box your masses and answer. Always do a mass check. Okay, M over Z 43. Just count it up, add it up, get a calculator and see if it's correct. The mass spec, even though it seems like it's randomly chopping up everything, every single proton and neutron is recorded here. It's a very, very sensitive machines. Nowadays, they have machines that will record more than 4 decimal places. So you even know exactly which isotope it is. Okay, it's been used a lot for detection of protein fragmentation patterns, DNA fragmentation patterns, air pollution, even in airports to see if people are carrying explosives and so. It's a very sensitive method, and it's widely used. In fact, the uses for mass spec is growing by the day. All right, so this is just some very basic concepts for organic molecules. Talk to you soon, guys, and I will see you later.